I think everyone working with effective population size know who he is. He has really moved this theoretical concept out in practical use. He has developed a multitude of methods in order to estimate this important parameter from genetic data. A lot of people in this room has been really involved in trying to understand how his models for how demographic variation affect the size of NE. He has looked at spatial variation, how that affects the estimates of NE. He has done almost everything on NE. So we are extremely happy that we were able to get him here. And it's very strange that you are so active, still a pensionist. So the chair is yours.
Okay.
Yes.
Well, thank you very much, Bernd and organizers for inviting me. It's always fun to come back to Trondheim. Been here several times. Always nice to see old friends, but also reminded how many really good scientists there are in Norway, and a lot of them right here in Trondheim. So this is not for this whole morning because we have two more speakers after me, but before the break, I'm going to give two talks, or I was asked to give talks on these topics. So first, a brief primer on conservation genetics. Then I think we'll have question and answer discussion session. And then practical considerations about estimating effective size with some more questions and discussions. So there's 45 minutes for each of these. I'm going to try to talk for about a half hour to leave adequate time for discussion. So that's the goal anyway. Before I get into the details, though, I have to do a bit of a digression because there's an elephant in the room, which is this question. Since I've been here, keep getting pestered by this sort of question. And the good news is there's really a very simple answer to this question, and it's really quite robust. And here's the answer. We have abundant empirical evidence that this is actually what's happening. The problem is, and the bad news is that all of this implies another question, which is, how is it that these people got elected not once, but twice? And that's a much more difficult question. I'm sorry to say, I'm as baffled as you folks probably are. I don't have any answers for that question. But that's enough about the US. We're going to move back to Europe here for the rest of my sessions. So I was asked to talk about conservation genetics. That's a big field, so we're going to condense things pretty quickly. But in general, one way to think about conservation genetics is a subset of conservation biology. And you can argue over how big or how small a subset it is. But one interesting point is that conservation biology is really a young discipline. If you ask people in the 1960s, say, you know, what is conservation biology? You'd probably get a blank stare. I don't think the term was even in use at this point. So this is one of the really important founding documents for conservation biology. I really like this one. It's a book edited by Michael Saleh. But the subtitle here is Science of Scarcity and Diversity. To me, that really captures important things about conservation biology. So scarcity implies a risk of loss. Certainly we're concerned with that here in this whole program. And diversity, there's lots of aspects to diversity. We're going to talk about diversity of genes, but you can also talk about diversity of organisms and habitats, processes, and maybe even solutions. So that's, I think, a nice context for thinking about conservation biology. Another way to think about conservation genetics is a subset of population genetics. And actually, this may be even the earliest founding document of conservation genetics, this influential paper by Otto Frankel in 74. So that's 50 years ago. Basically, he was talking about sort of a moral imperative for scientists to get involved in thinking about these things, how genetics was related to conservation of biodiversity. This slide I borrowed from Fred Allendorf. He's pointed out that you could make the argument that Charles Darwin was really the first population geneticist, because this wasn't at the time of Origin of Species in 59. But later in his life, he did things like a lot of breeding experiments with pigeons. He was, and the reason I think Fred made this slide was that later on he got involved with what we would now call genetic rescue. He was involved with studying the effects of bringing new blood into populations that were closely isolated and inbred. So that's just sort of an interesting historical background. Conservation genetics then, by the end of the 90s, had emerged or matured to the point where it merited a new journal. This is the idea of Russ Hosel, who's still the editor of the journal. And if you look at the guide for authors, it lists, this is just a non-exhaustive list of sort of topics that can be considered by the journal. So you can see it's a wide-ranging field of investigation. And in a half hour, there's no way I'm going to try to cover all of these. So we're going to zoom in here pretty quickly into things that are directly more relevant to discussions today, which is based on the recent developments, say 2020, in the Convention on Biological Diversity. We're looking at mandates for conserving and monitoring genetic diversity. And there was a lot of talk about those at the workshop yesterday, and more talk today, I'm sure. But before I go on, there's a lot of people who've been working hard on these issues. The main achievement of the 2020 changes was to get more explicit language about conserving genetic diversity into the Convention on Biological Diversity. And in that respect, I really feel it's important to highlight one particular person who's been doing this kind of day and night for close to 20 years, I think. And that's Linda Laker from Stockholm. So here's a nod to Linda. I think she may be tied in remotely, but, and this is not to diminish the work of anybody else. Like I say, there are lots of hard workers. But Linda's been particularly influential and tireless in her efforts in this regard. Okay, so if we're talking about genetic diversity, there's lots of ways sort of to slice and dice it. You can apportion it in different ways, but even if you restrict it to diversity within a single species, you can, the two major components then would be diversity among populations and diversity within populations. So most of the efforts today, I believe, are, and certainly in my talk, are going to focus on this within population component of genetic diversity. But as we'll see, that within population genetic diversity can be affected by interactions with other populations. So you cannot ignore interactions with other populations. But I'm not going to be focusing primarily, for example, on FST values between populations or things like that. So if we think about what shapes genetic diversity, there's 4 evolutionary forces we want to consider. Mutation is the ultimate source of all genetic variation. So it's indisputably very important. On the short time frames we're generally thinking about for conservation, though, generally mutation is rare. So in many cases, it's convenient to pretend mutation's not occurring over the short time frames we're dealing with. And in many cases, that's not an unreasonable assumption. Migration and selection are important potentially for all populations, but not all the time. And genetic drift then is a random process that affects all finite populations, which means it affects all populations on Earth, because it's easy to model infinite populations in a computer, but they don't exist in reality. So quick digression about selection. Selection works on phenotypes. Phenotypes result from the interaction of genes in their environment. So the phenotypic variance or the phenotypic diversity on the right there is a sum of components from the environment and genetics. And the heritability then is a fraction of total phenotypic variation that can be attributed to differences in genes. So it's this genetic variance in the numerator and the genetic plus environmental variance in the denominator that determines the narrow sense heritability, at least. I'm not going to talk more about that today, but that's mostly for context about selection. And to emphasize that it does depend on diversity in genes. There are a couple aspects of genetic drift that distinguish it from the other 3 evolutionary forces. So these other 3 forces all affect genetic diversity at specific parts of the genome, whereas genetic drift affects the entire genome. The entire genome is subject to some random forces, random noise associated with genetic drift and finite population size, whereas the others can affect specific parts of the genome. They're also true that migration and selection, they shape genetic variation in specific directions. Okay? Whereas genetic drift is a random evolutionary force. It's predictable only in its magnitude, but not direction. So, for example, we can predict with confidence that over time, small populations will see, on average, greater changes per time unit in allele frequency due to genetic drift, but we can't say in advance whether the allele frequency through drift is likely to go up or down. So there are interactions, of course, then, of these 4 evolutionary forces. Genetic drift interacts with all the other forces. So mutation creates genetic diversity. Genetic drift prunes it. So it's convenient often to talk about a situation where genetic drift and mutation have reached an equilibrium such that the amount of new genetic diversity created by mutation is exactly balanced by the amount that's removed over time by genetic drift. That's called equilibrium, mutation drift equilibrium. I said it's convenient many times because theoretical results are often obtainable at equilibrium conditions. But it's important to recognize that mutation drift equilibrium may actually be kind of rare in nature because it can take a long time to achieve mutation drift equilibrium. It's also true and important that genetic drift modulates the effectiveness of selection and migration, which otherwise would be essentially deterministic in infinite populations. You don't need a very big, very strong selection coefficient to have a big effect. But in small populations, random fluctuations in genetic parameters due to genetic drift can overwhelm a fairly small signal from selection or migration. So it makes the consequences of those otherwise deterministic forces relatively unpredictable. Situation is really analogous to a situation with gambling, say in casinos. You know, if you go to places where gambling is legal, say Nevada in the United States, every little gas station and little convenience store has at least slot machines or something you could put your money into and probably lose. But there are also large casinos that have huge volume. And the large casinos can't afford to get away with a very small house margin on each individual wager because there are so vastly many wagers done by so many people. They know that it's just a very small house margin with the law of it's like inevitable grinding down that the house is going to come out ahead. Whereas a local gas station or something, they could end up their whole week of slowly building up a little bit of profit could go out the window when someone hits a jackpot. So that's sort of like what happens in genetic drift in small populations. You can have these random things that make selection and migration difficult to predict consequences for. So the reason now that we're talking about effective population size today is the rate of genetic drift is determined by the effective population size, or at least I should say the expected rate of genetic drift, because everything is probabilistic with respect to effective population size and genetic drift. So that raises the question, well, what exactly is NE? And I've been struggling with that question. I have lots of people asking that question. You can find dictionary definitions or textbook definitions. Most people can, in this room, probably can recite them. I found them in general not being too illuminating. I mean, I could learn how to recite them, but they didn't really help me understand the concept. So I've tried to approach it in different ways. At its simplest, NE is just a number like N, okay? But it's generally smaller than the number of individuals. And the other important thing is NE it's not a number of things. It's an imaginary number. It's totally a human construct. And it's created by us to try to understand and quantify the important process of genetic drift. So census size and effective size try to capture different aspects of abundance with respect to ecological and evolutionary processes. So the demographic or ecological consequences of population size, those are captured by the census size, number of individuals, or maybe often the number of adult individuals, depending on what you're talking about. But things like competition, predation, birth and death rates, these all depend on the number of individuals Epidemiology also depends on that. For instance, in COVID, when people were talking about, well, when are we going to achieve herd immunity, for example? That would occur when a certain fraction of the population, certain fraction of the N individuals achieve immunity, either through vaccination or previous exposure or something like that. So there's lots of examples where N is really the primary importance. But the evolutionary consequences of population abundance, they all depend on what we call NE. And so this is the rates of genetic drift, rates of change of allele frequency, rates of loss of genetic diversity, rate of increase in integrity. Those depend on NE. So if you want to really understand both the ecological and evolutionary context of populations, you really need to understand both numbers, not just one of them. One of the things you can do then that's really valuable for effective size allows you to quantify the role of genetic drift, sort of as a null hypothesis. So you can say, you can ask the question, okay, how fast would genetic diversity be lost? Let's say as measured by heterozygosity, which is the probability that two individuals have two different alleles. The copies they got from their mom and dad are not the same. So it turns out from simple population genetics theory, we have this formula here that says the expected ratio of heterozygosity after T generations of total isolation compared to what you started with, H sub 0. It's just this, basically you're losing 1 minus, you're losing 1 over 2 NE, the fraction 1 over 2 NE, proportion of heterozygosity each generation. And this will occur, is expected to occur if there's no mutation, migration, or selection. So the other forces are absent. So again, this is a null hypothesis then that can be used to test. If you can measure the rate of loss of heterozygosity over time and see whether it corresponds, and you can have an estimate of effective size, you can see whether it's consistent with it. It might be that it's lost at a higher rate or lower rate than you expect by genetic drift alone. Then you have to consider, well, could that just be a chance event? You can use statistics to test that hypothesis. If you can't explain it by chance, then you may have to postulate the activity of some other evolutionary force being at least partially responsible for your results. So this is a really important way in which effective size is used to help postulate or formulate null hypotheses about genetic drift. So here's an example from simulated data of how this works. This is loss of heterozygosity over time in simulated populations. These had overlapping generations with a generation length of a little over 5 years. Whoops. A little over 5 years. So in 500 years, we got almost 100 generations of genetic drift. The formula on a previous page, and given the effective size that we knew the life history and what true effective size for this, that allowed me to predict this expected black line. And then for each of those colored trajectories, that's a separate run of the population, a separate simulation using just 50 tracking average heterozygosity across 50 SNPs, 50 diallelic loci. So you can see that the average across all of those is going to, if I calculated it, would correspond very closely to the expected result. But since it's only 50 SNPs in each trajectory, you can see there's a fair bit of variation. You could be a fair bit above or below the prediction just because of chance realization if you don't have enough replication. So as you get more and more replication of genetic drift, you should get convergence on the expected values that are predicted from theory. And there's lots and lots of examples for that. Those expectations have been tested and confirmed. Another really important thing to recognize about genetic drift is that it is inversely related to effective size. So this relationship then is very nonlinear. All aspects of genetic drift are basically a function of 1 over NE. So you get this curvilinear relationship, which means once effective size gets large enough, say 50, 500 or 1,000 or so, 1 over NE or 1 over 2 NE for diploids is a small number. And so genetic drift is pretty small, and it doesn't even go down too much more as NE gets really big. So it's just big enough to make genetic drift really slow. But as effective size drops below, say, a few hundred, and particularly if it drops below 100, 1 over NE starts to get much bigger, faster. And in particular, when you get down to lower numbers, the rate of genetic drift increases really fast. So that's why the whole field of conservation biology, conservation genetics, primarily focuses on this area of low effective size, where small changes can make a big difference into what the consequences of genetic drift are. Well, how do you know what true NE is? True NE is determined by the pedigree of the population. In particular, 2 most important parameters are the mean number of offspring. If K is the number of offspring produced by each parent, then the mean, K bar, and VK, the variance in offspring number, those are the 2 most important parameters in determining effective size. Apart from N also, which is total number of potential parents. And in particular, this ratio of variance to mean is really central. So you can see in this formula, if the variance and the mean are the same, the denominator is going to just be K bar. It's K minus 1 plus 1. And then if you ignore the minus 1 numerator, you have NE basically equals N. Okay? If you have variance equals the mean, well, that's Poisson variance, which is essentially what happens in random reproductive success. So that's random reproductive success, strictly speaking, produces binomial variance, but it's essentially equivalent to Poisson variance where the variance equals the mean. So it's convenient to pretend that random reproductive success produces NE equals N, and it's pretty accurate. But if the variance is greater than the mean, and that's generally true in real populations, then what we talk about that as the variance being over dispersed. That's going to create a situation where this denominator gets bigger and the NE becomes less than N. So this ratio of variance to mean is really important for effective size. Here's something that is not effective size, even though you can read about it in all sorts of places like textbooks or by people who should know better. Effective size is not the number of individuals that actually produce offspring in the next generation. That's true in some cases. It could be exactly the same, and in some cases, it's pretty close to that, but it's not true in general in any real sense. And I started seeing this in the last 5 or 10 years. It seems to pop up more and more frequently in the literature. It's like this whack-a-mole problem. You know, it comes up one place and you try to dispel that idea and it just shows up somewhere else. So I'm not sure what to do about it. Which effective size do we have to worry about? There's inbreeding effective size, variance effective size, and many others you can find described in literature. There are reasons people have identified all these that capture some nuances with respect to genetic drift. It can be important. But I would suggest for practical purposes, mostly you can forget about these. It's not so important to worry about whether you're estimating inbreeding or variance NE. For example, those two most common you're dealing with. It's much more important to figure out which time period you're estimating effective size for, because that's what you're going to do with the data and try to make sense of it. So that's what should be focused on. Here's an example, and I would say in general, particularly for demographic situations, inbreeding effective size is more practically useful than variance effective size. I'll briefly explain why here. This just shows that this cartoon value, you have n individuals, potential parents. There's some subset of n, not really a subset of individuals, but some theoretical concept relates to NE, eternally small. The offspring are produced, their genes come from this NE conceptual pool. And then some subset of the offspring become the potential parents of the next generation. So if you're going to estimate inbreeding effective size, you take a sample, say, of offspring, and that gives you information directly about effective size in the parental generation. Variance effective size gives you information about NE in the offspring generation. So here, that would be NE here. But in a computer, it's possible to pretend that these NE actually corresponds to some individuals. So you could actually model this in a computer and you could calculate the variance between allele frequency between individuals here and here. But in the real world, this is not an actual number of individuals, and you wouldn't know which ones are really producing the next generation anyway. So there's no practical way to sample the allele frequency in the offspring generation. So to use say the variance effective size estimator, say the temporal method, you have to compare allele frequencies in the offspring, say, of consecutive generations, or offspring of generations that are 2, 3, 4, 5 generations apart. So that's fine, but demographically, it's really not feasible to make much sense of variance effective size in real populations. Placing NE in context, there are some interesting quotes. This one from Dobzhansky is well known for a long time. Mike Lynch, I was told, had this quote placed on the door of his lab. Okay, and Fred Allendorf has sent me emails that make this claim. Nothing in population genetics makes sense, except in the light of NE. Okay, so this just goes to the potential importance of effective size. How do you really grok or really understand in depth, intuitively effective size? To me, the best way is think about a lottery. Here we have to think then about a lottery where the winners get to produce the offspring for the next generation. And each offspring has to have a lottery to decide who its parents are going to be. Okay, so there's 2 parents, so you have to have 2 draws. It's like drawing names out of a hat. Now you can think about specific cases. If you have a situation where everybody has the same number of tickets in the lottery, then you have what's called an ideal population. That means the variance is on average going to equal the mean, and you're going to have a situation where where effective size equals census size. But in most real populations, that's not the case. Some individuals have more tickets and they have a better chance of winning the lottery to produce offspring for the next generation. That's kind of like capitalism. And so that again, then this disparity in expectations, this disparity in expected winners and losers in the lottery, that is what reduces effective size. Even if everybody has the same number of tickets, if you do a bunch of draws, some individuals are going to get picked more often than others just by chance. So there will be diversity in outcomes, even if you have a totally fair lottery. What we're talking about here is even before the lottery starts, some individuals are definitely more likely to be winners than others. That is what reduces effective size. And there are quite a few factors that can cause that. First is separate sexes. If you have two sexes, then you have to have two lotteries. And if the numbers of males and females are different, then the members of the less numerous sex on average get picked more often. Because every individual has one jet. So this creates disparities between males and females in average offspring number. That reduces effective size. That's got a lot of attention, but in fact, sex ratio has to be pretty extreme to have very much effect on the NE to N ratio. So to get a really small NE to N ratio, you have to have other factors. They can be things like fitness differences, just the fact that some individuals are bigger, stronger, faster, sexier, or whatever. And they basically, that gives them more tickets in the lottery. They're more likely to be parents. Age structure, if you have interoperospecies, one's individuals that happen either by design, by having good genes or good luck, they live a long time. They get 10 or a lottery every year to see who gets to produce offspring. So they can increase their lifetime reproductive success that way. And some individuals by chance may end up in better habitat, not because of any intrinsic thing about them, but just because they happen by luck to end up there. And if those better habitats make them bigger, stronger, whatever, they may produce more offspring. Not because of fitness, but just because of luck. A combination of and heterogeneity. How big does NE have to be? Well, this 5,500 rule is pretty well known. Short term, the guideline is 50 individuals just based on empirical data from livestock breeding. They found that generally in the short term at least, livestock populations can tolerate something like 1% increase in interbreeding over short periods of time. The 500 is developed based on some original theory from Drosophila, a balance between mutation, gained by mutation, and loss of edited genetic variation by genetic drift. So that's the origin of the 55 NE500 criterion we're going to talk about. There has been back in the 90s, I think Lynch and Landy proposed this mutational meltdown idea. The idea was that in totally isolated population, you could get a buildup of slightly deleterious alleles that cannot be eliminated effectively by selection. But this one particularly applies to really totally isolated populations. So people have largely ignored it these days. I should point out that Dick Frankham and some of his colleagues think that 5,500 should be revised to 100,000. That's not a scientific consensus. So I think probably most people have still sticking with the 500, 5,500. So that's just a FYI. But there could be developments on that issue in the near future. Here's one of the most important points we want to talk about today. This has to do with migration. We're talking about the amount of genetic diversity that we maintain in the local population. It turns out there's a huge effect of migration, even small amounts of migration. This figure shows results of simulations of situations where I think there were 10 populations of 50 ideal individuals each. And if you look in what's shown is the average heterozygosity averaged across all the individual populations. And you can see they all started with a high level of genetic diversity in the simulations. And they lost genetic diversity until they reached a balance between migration, mutation, and genetic drift. And with totally isolated population, this is the number of migrants, actual migrants per generation. You reach a level less than 20% heterozygosity. But if you allowed even 1/10 of a migrant per generation, one migrant every 10 generations, you can see you've got twice the level of heterozygosity in a local population. And if you have one migrant per generation, which still has really large FST values, you have 3 times as much genetic diversity. And you have essentially as much with something have 5 migrants per generation. You have almost as much as you would if the whole population were pan-mictic. So this tells me that if you're talking about the NE500 criterion, you should be applying that to local populations only under really extreme isolation for long periods of time. Most other cases, there's really strong effect of interaction with other populations. So you really have to think about effective size of metapopulations. Now, many of you will have noticed that since 2020, there's a whole slew of important papers that have talked about various aspects of these genetic diversity monitoring criteria. So here's a selection of 6 or 8 of them I found. These all discuss the NE500 criterion, but they don't, none of these, as far as I can tell, mention metapopulations. But there is this one that does, and it states explicitly that the NE500 criterion should be applied to metapopulation NE. So, whoops, that's really important, I think. But I think it's unfortunate. These are all published in peer-reviewed papers. They aren't just reports, something. So I realize you have to worry about how much nuance, geeky nuances you can present to policy people. But I think it's important to get some more consistency in the scientific literature about this issue. Or if there's more discussion that needs to be made, it'd be important to have that. So this is the last thing I want to talk about in this section of the talk. What is metapopulation NE? That's a complex topic. There's quite a few papers been published, but there's no single resolution, really. We can use sort of as a point of reference, well, what if, let's just say, metapopulation NE is the sum of the individual NEs. And that's what the purple line there is. That's, I think, what the Genomo program has adopted as a working hypothesis. But if you use Wright's Island model, it actually produces metapopulation size that exceeds that. But that's entirely attributable to really unrealistic assumptions of Wright's Island model. So if you look at more realistic models that allow for things like extinction recolonization, or the fact that populations might change in size over time, there might be differences in productivity or asymmetrical migration, those models generally show that metapopulation NE can be less than the sum of the parts. Okay, so this is really important to try to, maybe it's time to renew evaluation of this to see if things can get resolved a little more clearly. Okay. So I'm going to pause now and see if we can have a little bit of time for discussion questions in this before talking about estimating any.
So we have to use the microphone.
So thanks for a very nice talk. When we think about the meta population, wouldn't this 5,000 values, so their mutational meltdown can be a problem? Or what is your, then 500 seems quite low for a criterion, or?
So is the question, if you're talking about the entire meta population, is 500 too low? Is that the question?
Yeah, I was thinking about this argument of the mutational meltdown being a problem by Lynch and Landy, and that seems to be to have relevance for the NE of the meta population, right?
Okay, I see. So the 5,000 criterion, the mutational meltdown idea. So if you consider the meta population is isolated from other meta populations, maybe, yeah, it's an interesting idea. That's worth thinking about. I just, the mutational meltdown idea gained some traction in the 90s, but frankly, I haven't heard much about it in the last 20 years or so. So maybe it's worth thinking about in the meta population context. Yeah, that's possible.
There are more questions.
We can have questions at the end too.
Yes. Maybe are there some questions, Anja, online?
No questions online so far.
Thank you so far. Robin, we will change the presentation.
Okay.
There is a question, if we can still have it.
Can we have the question?
Sure.
Okay, I will just, Joachim, I will just read out what you wrote. And okay, well, we're not supposed to let people talk. Maybe, Joachim, can you ask in the end after the second part of the presentation, maybe?
Okay, so you want to defer it? Is that it?
Yeah, I think he's still typing.
Okay. Okay. All right. So let's go on. So now